I want to present to you today the dirty Meerkat. When I first walked into this room yesterday, I was a little bit scared because of the size of the room and everything, so I don't talk a lot, but and the second thought I had was actually, hopefully I did my research well, because I'm talking today about limitations of Suricata. So that's a kind of a dangerous topic in this room, but still I think it's worth it, and everybody should know also limitations of the tool that he or she is setting up and operating. Still, the good news is I think that Suricata still does a great job in analyzing load-balanced and asymmetric networks, because there are lots of tools outside there. They are doing a lot worse than Suricata does. I think really Suricata is on top there. And I'm also excited because Victor yesterday already announced for the new version that maybe some things I present today will be fixed in the next release. So let's see and what happens during the next year then. Short introduction. I'm a freelancer doing lots of projects in the telecommunication and industry, network forensics and legal interception. Had done lots of stuff in satellite networks, and satellite networks work a lot different than cable-based networks. Yeah, so also for Suricata, most probably you have to do some quite weird stuff in order to get things out that you want to control or monitor or whatever. The best thing to get in contact with me is via email. I also have social media accounts, but I'm really bad at social media, so if you want to get in contact with me, just drop me an email. Okay, let's jump into the problem. I want to talk about load-balanced, aggregated, asymmetric routing, more or less about links where one single flow is spread over multiple links, multiple physical links. Yeah? To an extent, for example, in satellite-based networks where we have the client-to-server communication completely separate on a different link than the server-to-client communication. So this is what the problem is all about. For sure, if we want to analyze the traffic, the best thing would be to have clean, full-duplex traffic on a single wire. And the first thing that comes into mind for sure is merging the traffic. So when we have, for example, two tapping points, then merging the two tapping points together would generate us hopefully a clean full-duplex traffic on a single wire. But we might run into problems with that. I talked to Christian the other day actually, and he said some quite true words, because in complex networks it's sometimes really difficult to find clean tapping points where you can aggregate traffic that really makes sense. So you might end up with traffic duplication if you have two physical links that are merged together, where some traffic is on both of the links. So you simply merge them together, you get duplicate traffic that is not more or less duplicated from the transport layer, but is twice on the link itself. You might get out of order packets, meaning you have, once again, two tapping points. The lines are, the cables are of different length. The transceivers have different behaviors in times of latencies. You might end up with seeing things like you have a TCP packet or a TCP acknowledgement that comes in front of the actual TCP data packet. So you have this is what means that you have out-of-order packets. You might even have packet loss. Yeah. So once again, if you want to merge traffic, you have to feed it into a switch, or into some device that brings it together, the first thing a switch does when it is overloaded, it drops packets on the span port, yeah, because that's the port that is not needed at all for normal operations. So when the CPU is overloaded on the switch, you simply lose packets. And sometimes it's even not possible to merge them together because of local limitations or bandwidth limitations. So if you have 40 gigabit links, 100 gigabit links, there is simply sometimes no way to merge them together because we don't have technology yet for 200 gigabits on one link. So this smart little guy then comes up with an idea. How about analyzing the dirty traffic as it is on the wire? So, and we will jump into that topic and see what we can make out of it. What I want to show in this presentation is single-sided traffic analysis with SuriCata by example. So I will present more or less 2 examples. We'll play around with these examples, and I will show you what SuriCata does with the traffic. I will show you how to deal with out-of-order packets. Of course, tips and tricks for single-sided traffic analysis. So I will really, I'm looking forward to seeing the reactions of the rule writers, because you need to do lots of stuff in rule writing there, which would be considered in normal traffic. It will be considered more or less that there are bad rules in normal traffic. This presentation doesn't cover performance issues. One word to performance issues. If you analyze dirty traffic, you have a performance trade-off, because SuriCata has to do lots of additional analysis there, and you lose performance there. So that's one thing on performance. I won't go into detail in this presentation. Everything is tested with a late development version of SuriCata 4.1.0. So I wanted to be in this version because I don't want it to talk about old stuff there. So this is really tested with the newest version of SuriCata. And I need to talk about configuration a little bit now. There are actually 2 options in the SuriCata configuration which are disabled by default. This is the midstream configuration and the async one-side configurations. This is in the streaming section of the SuriCata configuration. The midstream does the following. It enables us to more or less ignore for example, TCP SYN flags or whatever, and analyze traffic which is, so to say, dirty. So we don't care about TCP handshakes, we don't care about anything that happens there. If we see a packet, then we will process it and send it through the engine, no matter what it is. The async one side is a flag that enables us to control flow states. Usually, when we see a single-sided traffic, we won't get into an established flow state, yeah, because we don't have the normal handshake, or we don't have double-sided connectivity and streams in UDP. So usually, we would stay in the new state in the flow. Async one side does the following: if we have at least 2 packets in a flow, we will directly jump to the established state in the flow without any other thing. So we don't, once again, need TCP handshakes or whatever there. We simply jump into the established state in the flow there. So in order to wake you up a little bit, where are the rule writers? Not many rule writers there. Who uses flow variables or knows about flow variables? Okay, some. Good. For the others, actually, flow variables are quite handy when it comes to extracting content out of the flow and directly moving it to the if.json file. So I will come to the regular expression later when I'm using it, but the essential part here is this in the regular expression, this flow keyword, which allows us to extract everything that is in the brackets and directly submit it to the if.json for further investigation. So let's go to the first example. I've chosen DNS because that's quite a simple protocol, and we are analyzing. I hope you can see that. We are analyzing a normal DNS query and answer session. So we are concentrating on two events there, or two types of events in the if.json file: the flow events and the DNS events. So what would you expect when you see such traffic? For sure, you would expect three entries there. One entry for the DNS query, one entry for the DNS answer, and a flow entry with an established flow. And of course, this is what we get. So we see the DNS query here, which is highlighted, the DNS answer, which is highlighted, and an established flow. And the application protocol is DNS. So let's play around with this sample a little bit. The next thing, obviously, if it comes to single-sided packets, is we want to analyze the DNS query only. So this is the PCAP, only one packet, a DNS query, and what do we expect? We for sure expect a DNS entry in the if.json file which shows us the query, and we would expect the flow. Maybe the flow is not established because we only have one packet, but the flow should still be there. And yeah, that's what we're getting. We have the DNS query there highlighted, protocol is DNS, and the state is new. Obviously, the next thing what we want to do is processing the DNS answer only. So once again, one packet, the DNS answer. The expected result would be that we have one DNS entry for the answer, and once again, one flow entry. And this is what we're getting out, actually. So the answer somehow vanished. The thing there is, you can see it highlighted that the application protocol identification failed. This is more or less due to the detection ports that are configured in the if.json file, which more or less are tested against the destination port of the packet of the DNS flow. So we have only here the server to client connection, meaning that the destination port is not 53 in DNS here at the destination, but it's on the source. And this is why we don't get the DNS answer here. Yeah, so analyzing DNS answers only won't get you DNS information because the application protocol identification would fail. And the next thing is we want to check what happens when we have the wrong timing. So we have another small sample here. The only thing that changed here from the normal DNS query is we just flipped the answer and the query. So the answer comes first and the query comes second. Once again, we should get 3 entries there, one for the query, one for the answer, and a flow entry. And this is actually what we get out. So there is obviously no DNS output because once again, the application protocol identification fails because we have the server to client connection first, and after that, it's not checked anymore if we have a client to server connection. So we lose the DNS information when we flip packets there because the flow is not built up correctly. So, what we've learned so far. Flow state and application protocol detection matters. Single-sided flows math with those under certain conditions. So it's better to have the client to server. You get out more if you have the client to server connection. If you get less because of these identification problems if you have the server to client connection. The network packet order methods, because it can be that if you are starting with the wrong packet in the flow, it can mess up all the information that you are getting. Yeah, so out of order packets are really bad when they occur, especially right on the first packets of a network flow. Layer 7 protocol or layer 5 to 7 protocol analysis is quite hard when it comes to single-sided traffic. There are plugins that work better. There are plugins that don't work as good as they should, I believe. DNS, as you saw, works for client-to-server communication. HTTP heavily relies on the communication in both sides, so HTTP is kind of a mess. TLS is better, so there are certain limitations in the layer 7 protocol analysis that you should be aware of if you do single-sided traffic analysis. And of course, if you're using the default rule sets, for example, from emerging threats, you should also be aware of that some of the events will fire and some of the events will not fire if you're analyzing single-sided traffic or dirty traffic. And the question is there anything left we can do? Probably yes, because otherwise I won't ask this question, yeah? We have another sample here. It's simply some FTP commands sent there. We have on the left-hand side the output of the follow TCP stream of Wireshark, so you kind of see what happens there. And we have this one alert that I showed you earlier. Please don't deploy that alert in a live environment because it's only going on, it's actually matching on all the traffic and it's only executing one regular expression, but actually it's very good to show the point that I want to make here. So what we are doing there is we're simply watching the client to server traffic here, the commands that the client is sending to the server, so this means the red part of the FTP session. And we are checking on the FTP commands. The things that we should get here is if we do flow analysis, we should get actually the first entry in our flow variable, the authentication TLS command. Because if the alert fires once in the flow, then it will not fire again. So this is what we would expect, and this is what we are getting out. So in the default scenario where we have both sides of the traffic, we generate the alert, we are getting out the flow variable, the authentication TLS command, and of course the application protocol is FTP. We have a flow document which says that the state is established, so everything is nice here. Obviously what we want to do is run this alert on single-sided traffic. So the next PCAP in there is only the client-to-server communication. So we only see in the follow TCP stream, we only see the red part of the traffic. And obviously, we would expect that the results are the same as in the previous example. And actually, this is what we're getting out. So it's more or less we're getting out all the commands that we searched for. Yeah, not only one command, not only the first command, but all commands. And you can see that we have a pcap count in there. So when we analyze single-sided traffic, we are more or less analyzing on a packet per packet basis and not longer on a flow basis. Yeah? So this is very important for alarms and also for rule writing on single-sided traffic because we are not, as I said, we are not longer analyzing flows, we are analyzing on a packet per packet basis. You can also see in the flow down there that as we use async one side, that the flow is established, but still it's on a packet per packet basis. So some more findings here. Layer 3 and 4 analysis for single-sided traffic is better than layer 7 analysis. So we can do lots of things based on IP, TCP, UDP, and ICMP alerts. The most important thing is that the payload analyzed is on a per packet basis and not based on flows anymore. The good thing is that out-of-order packets don't matter anymore, are not obstacle anymore, because as we are analyzing on a packet per packet basis, if the packets are switched or if they are out of order, only the alerts would be out of order, but the alerts will still fire. And also the important thing is that if we want to analyze single-sided traffic, it's very important to write rules that are more or less on a few bytes in the traffic. Because if the traffic is spread, or if we look on traffic that is spread over 2 packets or more packets, then we lose the alert. So this is the whole thing there. Yeah. So that's all from the Dirty Meerkat so far.